Good afternoon, everybody, and welcome to this special AIMS public lecture. My name is Naina Ralaivosona. For those who haven't seen me yet, been around, and I'm truly honored to chair this session today. I'm originally from Madagascar. I'm an associate professor in the math division here at Stellenbosch University. And most importantly for today, I'm an AIMS alumni. Since this event is a part of AIMS alumni engagement program, I've been asked to briefly share my journey with you, if you'll allow me. I was a student at AIMS, like you guys, 20 years ago. That's a long time. 20 years from now, I'll be close to retirement. I'm giving too much. Anyway. After that, I did the maths tripos at Cambridge University and then a PhD at Stellenbosch University, which I completed in 2012. And since 2013, I was a lecturer here at Stellenbosch University. But I maintained my link with AIMS. AIMS is like a home to me. Over the past 10 years, I've been teaching courses there. I've continuously doing the mathematical problem solving. The last one was in October. Do you guys remember that course? Who attended my course? Those are the cool guys in the room. I also taught other courses there, 2 other courses. And you might have seen me as well this week because we had the privilege of hosting our LMU Munich University and Stellenbosch University collaboration workshop. This week at AIMS in the Monday, Tuesday, and Wednesday. So my visitors are here as well today. So I've really maintained my link with AIMS, and it really is incredible to see how AIMS grown over the years. So AIMS started in 2003. I joined in 2006, and it's incredible to see the changes that happened to the institute. I don't know now how many of you are here, how many students are here. The only indication that I have is how long the queue for lunch is. But on a more serious note, my message for you today is, stay connected to you guys, current students at AIMS. Be involved in this wonderful initiative. There is always something that you can contribute to this. Okay. So now for today's event, it's a collaboration between AIMS and NITheCS. Fortunately, the director of AIMS is here. She will talk to us a bit later. But the directors of NITheCS will come a bit later. So we will we'll give some time for him if he comes to explain what NITheCS is. Okay, now for the main event. It is my great pleasure to introduce our speaker today, Dr. Michel Winckler. When I read the bio I received, it's very long, and I say, which one can I cut? And I realize all of them are quite important, so I'm just going to go through them. Dr. Winckler is the administrative director of the Interdisciplinary Center for Scientific Computing, IWR, at Heidelberg University. Which is an independent research center with more than 550 scientists and staff, strongly rooted in mathematics and computer science. It's very much similar to what we do here. He studied mathematics at Heidelberg University and the University of Sussex, and completed his PhD at IWR in the optimization of engine components. So it's very much applied, have practical applications. He visited Agron National Laboratory and the Iowa University. Since 2007, he has also served as the administrative director of HGC MathComp, the doctoral school of mathematical and computational methods at Heidelberg University. In both roles, he had focused strongly on building international research collaboration, which is very important to us. He has developed an extensive network of partnership in Southeast Asia supported by the Erasmus Mundus exchange programs, and is actively involved in 4EU European University Alliance, where he presents Heidelberg in the research flagship of modeling and data science of the Alliance. And currently one of the two speakers of the network. The other speaker is Fabien Pazuki, that we know very well. I have a very strong collaboration with the math division here at Stellenbosch University. In fact, he was just here a few weeks ago. So since 2016, he has also developed close cooperation with AIM South Africa and is the Heidelberg coordinator of the Hey AIMS project, funded by the state of Baden-Württemberg. I hope that I get that right. Yeah. Close enough?
Yeah, very good.
To the limit. Anyway, he currently coordinates the Heidelberg University Africa Research Hub. So there will be time for us to mingle afterwards, so we can ask him about all of these wonderful things, which are promoting the institutional partnership across the continent. He gave a public lecture similar to this one 2 years ago, I think. Yeah. About, and in which he talked about mathematics and origami. I regret missing that talk because it looked very interesting, but I'm so happy that I'm here today to listen to you talk. So please join me in welcoming Dr. Michel Winckler.
Thanks a lot, Nena. I currently have some problems here, which you cannot see.
Just click on your slides, just do one click.
Yeah. No, it's the... there are some windows open in front of that. Okay. Fine. That one and the presenter. Oops. Yeah. Okay. Thank you, Nena, for introducing me, and thank you all for being here. I'm honored and a bit nervous, actually, giving a lecture in front of all of you. It is a public lecture, so one note ahead of the talk. For the mathematicians in the room, I will explain some mathematics in layman terms. If I'm not 100% precise, and you might raise your hand and say something, if I'm almost precise, then that's probably good enough for a public lecture. And for those who don't know too much about mathematics, and there are some in the room, and you will see some sentences in mathematics, some gibberish and whatever, wait a minute or so, and I will explain in layman terms what I want to talk about. So what I want to talk about, actually, is patterns and tessellations. And before I do that, I give a one-slide introduction of where I come from. Heidelberg University, what you see here is the Mathematicon, where we all come together to do mathematics and computer science. Heidelberg was founded in 1386, so it's the oldest university in Germany, and one of the oldest on the continent. We are a small city and a large university, so unlike our colleagues from Munich, we are from a city with only 150,000 inhabitants, but 35,000 students. If you count together the staff and the largest university hospital in Europe that we also have, probably every third people in the street that you meet is a university person. So that really shapes our culture. The Mathematicon hosts both the Department of Faculty for Mathematics and Computer Science and the institute that I'm representing, which is the Interdisciplinary Center for Scientific Computing. We are doing mathematics in real applications, so a third of our people are mathematicians and computer scientists, but the others are from astronomy, biology, medical, technology, whatever, but also art history, arts, law, and so on. And we are looking for mathematical applications in all of these sciences and research fields. So that's about that. And now a general introduction to what I want to talk about. What are tessellations? Tessellations are a way to tile the plane. So when a mathematician speaks about tessellations, he also almost always thinks about an infinite plane. So going from here into infinity in all directions. And the question is, can we come up with a rule, regulations, an algorithm to put tiles on these planes so that we are not overlapping the tiles and we are not leaving holes. And this is called a tessellation or a tiling. Names are a bit shady here. In Germany, when you think of tessellations, it's more like dividing the plane into areas. And you think about tiling, it's more laying tiles on the plane to get an infinite tiling, like a craftsman would do. So here is a definition. Tessellation is a covering of a limited or unlimited space, so only this room or until the end of the universe, with geometric shapes. Usually, mathematically, tessellations have this plane in mind, but you could also take a sphere and try to tessellate a sphere or a circle or whatever. And a tiling is also such a covering, and as I said, the difference is more like how you look at the things. Are you subdividing the plane, or are you kind of playing a puzzle game? And both concepts mathematically imply that those elements don't overlap, which is not true, because if you take two tiles, they are, mathematically speaking, closed forms. So if you would fit them together, there would be some gap in between. So what are you allowed to do? Well, you're allowed to overlap the edge. So the edge of a tiling belongs to both tiles, so to say. That's the only overlap that is allowed, but no overlap inside. And with the shapes, we are usually also restricted. So you usually don't talk about shapes that have a hole in the middle or that are kind of not hanging together. So you could have a shape with a half ball, half a circle here and half a circle there, and you would say this is the same shape belonging together. So in tiling, you are looking at something that is, well, a square or a circle or whatever, but without holes and not and hanging together. Mathematicians, to come up with ideas of tiling and to do that systematically, are always trying to characterize their task. So one thing is, can I come up with all tilings? Can I come up with a list of all tilings? In group theory, that was a big thing in the 50s or so, coming up with all simple groups or all groups of this or that type and counting them and making a system out of it. And the same is with tiling. We come up with certain lists of tiles and asking ourselves, is a tiling possible? How many tilings are possible? And so on and so forth. This helps us, this structure helps us to keep an overview and also subdivide the fields in areas where we do our research. And if you make the most rigorous assumptions, then after this slide we are done. So what we call regular tilings are tilings where you use only one shape, and this shape has all the symmetry that you can get. Yeah? All elements are equal, and you could take any vertex and any second vertex in this tiling, and they are also in a way equal. I know that mathematicians would not like that definition in a way. The mathematicians would say a tiling is said to be regular if the symmetry group of the tiling acts transitively on the flag of a tiling. And the flag consists of a face, a mutually incident vertex, and a mutually incident edge. So that's the mathematics definition. And in layman terms, that means if I go back one slide, and hopefully it works. Yeah, here we are. If I take this tiling, for example, I could take one element of the tiling. Oops, it's a bit difficult to do that. One element of the tiling. I take one edge of this element, like so, and I take one corner, which we call vertex, of this edge. And this is what we call a flag. And then we would search for another flag here. So this element with this edge and this corner. And then if we put one on top of the other, then every element in this tiling would end up on one unique element of the tiling. So it's kind of moving one to the other or finding a symmetry operation that puts one on top of the other. And this is what is meant by the sentence, acts transitively on the flags of the tiling. So mathematics try to be very defined here, and in layman terms, you can understand what it's all about. So regular tilings, you saw the whole list, 3 exist. So people came up with the term semi-regular tilings. Semi-regular tilings mean you can have different elements, but you have only one sort of tiling, meaning that any corner, any vertex in any of these tilings is identical with others in the same tiling. I try to explain that maybe on this example. There are these large octagons and there are these small squares, and any vertex that you take, like this one, is the vertex between 2 of the octagons and 1 of the squares. In the very same way, any other corner on this tiling is in the same way a meeting of 1 square and 2 octagons. So there is only one type of vertex, but there are 2 or 3 types of elements. And this is sometimes hard to see. For example, in this one, there is only really one type of corner. It looks very confusing, but every corner in this tiling is of the same sort. It's 1 green element meeting 2 red elements and 1 yellow element in all the same fashion. And then again, we have this idea of I take one of these corners, I put it onto one other corner, and when I do that, all of the tiling ends up identical on the other copy that I was starting with. And again, this is all. These are the only 8 tilings that you can do under this regulation. These are all the semi-regular tilings that exist. You would think, oh, I can come up with other versions of, but mathematicians usually start investigating that and then trying to show that no more are possible, and this is the final result. And for semi-regular tilings, that's all that there is. But of course, if we loosen up the regulations, we get more tilings. So here we are. That is 2 uniform tilings on the left-hand side, for example. What is a 2 uniform tiling? This one is a 2 uniform tiling. Now we have several different elements, and we have 2 types of vertices. There is this vertex where 6 triangles come together, and there is this vertex where 2 yellow triangles, 2 red squares, and 1 of these greenish triangles come together. In all of the tiling, you only will find these 2 types of vertices, and you can put any 6 yellow vertex on any other as a symmetry operation, and you can put any of the other vertices on any other. So this is called a 2 uniform tiling. On the right-hand side, you see a 3 uniform tiling. So we have 3 different types of vertices on the right-hand side. It's even harder to see, but you have this one, again, the 6 triangles. You have this one where 2 of 6 triangles meet with 2 squares and another yellow triangle. And you have this one where 2 yellow triangles not attached to a sixer, 2 squares and a single triangle meet. So this one and this one look much the same, but they are not. They are different types of vertices. So, and again, mathematicians are counting, and actually the one on the left and the one on the middle are sorry. They are 2 uniform tilings, and a total of 22 uniform tilings exist. No more. List is finished. And then there are 3 uniform tilings, like the one on the right, and 61 is the count, and also this list is finished. And you can go on to 4 uniform tilings, 5 uniform tilings, whatever. So there are more lists, but we know a lot about that, and you can go to several Wikipedia pages and look up what currently is known about these tilings, which lists are finished, where do we know more about it. Again, if you loosen up the equations more, if you give more leeway, then you get to more tilings. Pentagon tilings, you see this one on the left. That was discovered in the last 30, 35 years, I would say, maybe even a bit earlier. Pentagons that can completely tile the plane. It's only one pentagon each time. And this pentagon is put together in a family of pentagons, in this case 12, and these 12 repeat over and over again. How can I explain that to you? I tried again with one vertex. If you look at this vertex, you see that the light red and the blue are meeting with the yellow, and the yellow has this right angle corner meeting the two others. Is there a different one? I was preparing that and now I don't find it. Oh, here, yeah, almost lost it. Down here. So there are again, so the dark red one is meeting two others, but now two of the rectangular or right angle angles of pentagons from the blue below and from the light red above are meeting. Oh, the better version is here. Here you see it. Yeah, it's again three pentagons meeting, but this time two of the right angles meeting are with a line. So this is a T-shaped corner, and this is more a V-shaped corner. And if you analyze it properly, you will see that there are 12 tiles hanging together, and those you can repeat over and over again. No one said that all of the edges have to meet in corners. So look at this, and we already had that in the last one. If you say, okay, the edges don't have to align all the time, but sometimes they have an overlap. So you get a T-junction. If you loosen this up, you get tilings like the one in the middle. Or you take a tiling that you already have, like the one on the right side, which was a hexagon tiling, and you start to make the edges thicker. You get these edge elements, and that's a different tiling. I mean, you have now not only the regular tiling, but you have these vertices that only the edge elements form. So you get more and more tilings and more mathematics, and some people are investigating where does that lead us. There are parallels to crystal structures and whatever. So mathematics is very deep here, and most of the time don't expect a direct application. This is groundbreaking research, and mathematics is developing. Mathematics is the structure of patterns, and these patterns can be very well described with mathematics. But they also go into craft and art, and I show you a bit. We are looking at something very easy now. Again, we take a parallelogram. Oops, here. I'm supposed to point here. Here. Parallelogram. And we just take a line to subdivide it. That's a bit like with parallelograms, you can tile the plane. You just take parallelograms after each other in lines and in rows and in columns, and it works. By subdividing them, it looks more interesting. And indeed, this shape that you see here actually has a name in tiling. That's called the Sphinx tile. It consists of 6 triangles, equilateral triangles. If you have a bit of a two-dimensional analysis, you will see if you cut away, if you cut away this top, that's one of the triangles, and the bottom consists of 5. And you can put 2 of them together and then make a parallelogram tiling. Nothing much is happening, but it looks on your bathroom floor, it might look more appealing, this one, than if you would just take regular tiles, parallelogram tiles. We meet this shape later because it has a very important role in one of the latest developments of tilings. So that's an easy way to make a first craft. The Romans already knew that, and this is called the Roman pattern. So when you make it easy for your craftsmen people, what you do is you take some rectangles and some squares and so on, you glue them to a square, and you produce a lot of these squares. And then your bathroom can be covered with these squares. But it looks more interesting because it's not only these squares, but they are subdivided. But the human is incredibly good at finding patterns. So you will find these lines and these rows of your squares when you look at your bathroom floor. So Romans, actually 2,000 years ago, came up with an idea. And they were taking, okay, here is a square that is subdivided. I cut a bit away here, and I add it up here. I cut some pieces here, and I add them over there. And what you get is almost a square, but this nose will fit nicely into this hole, and this nose will fit nicely into this hole. So again, you just have a square covering, yeah, but just the noses fit in. You just take this, and the next you clink it in, and so on. And what you get is the tiling over here, but you don't see the square pattern anymore because these long lines are gone. And these were the rules for Roman patterns, and there was a lot of development on that says avoid crossing seams because eyes will notice crossing seams and they will see the regularity. Avoid seams that are longer than a meter. You have to think that they are covering like large planes in front of some buildings and so on, so a meter is quite long. And no two identical tiles next to each other. So if you have squares next to each other, at least shift them by a bit. And you can see this, for example, here, there are two squares and they are next to each other, but they are shifted. That looks much nicer than aligning them like so. So this is the Roman pattern, and this is how it looks on a floor. Mathematically, that's fine. Craftsmen have a lot of problems with that. And the reason for that is that on a floor, you don't only have the tiles, you also have the seams. Now, if you go from here, the bottom, to here, the top, along here, you can count 1, 2 seams. If you go from here to there, 1, 2 seams. But if you go from here to there, 1, 2, 3 seams. Each seam has a thickness. Yeah? And at one point you have to include 2 seams and in the other 3, so they cannot have the same thickness. The seams, but the seams should have the same thickness. So what do? There are 2 solutions, practical craftsman solutions, which mathematicians never need because there the tiles fit together without a seam. Sorry. What do? Well, either these yellow elements, when you fit them in, you make half a seam. If you watch closely, it's only these yellow 1 by 1 squares that make the problem. And when you fit them in, you make everything else, and when you fit them in, you put them to the middle, and then if every seam is 1 centimeter, then those around the yellow ones are only half a centimeter. And you will never notice because the long lines here are not broken. Here you will see a bit of a hiccup, but that's a small price to pay. Or you give these craftsmen smaller tiles for the yellows. So they are not 10 by 10, but they are 9.5 by 9.5. You make all of the rest again, and you put those in, and they are a bit smaller than the other 1 by 1 or 10 by 10 elements. So these are regular 10 by 10, and these are 9.5 by 9.5. And you get the half centimeter, or 9 by 9, you get the half centimeter on each side that you need for the additional seam. So that's when craftsmanship meets ideal mathematical concepts. You somehow have to make compromises. Tessellations also come up for kids. So we did that with Zenobia and NITheCS last year for the Day of Mathematics in schools here in Cape Town, and also in a school in Heidelberg, a primary school in Ladenburg to be precise. We started out with a square, and everybody knows how to tile the plane with squares. And then we were starting to cut away. At the corner B, we were cutting away a piece. and down at corner D as well. And then we were gluing them to the back. And then at the bottom, we were cutting away a triangle, and we're putting it up a bit to the right side on top. And still you can, because what you were cutting away at the bottom just fills up the top, you can still tile the plane with these elements, and you can make them look like, I don't know, fish in this regard. So here, because you were taking this triangle and moving it a bit to the side, when you have one row of fish, the next one has to move a bit so that it fits in the corner on the bottom fits to the corner shape on the top. So it's a moving element. And I did that myself as well. And if you want to try it out, it's really a nice pastime, like entangling or so. You can try it out for yourself. Start out with these forms that try to mimic a bird, or you take a triangular tiling and you subdivide each triangle with 3 lines. Then you make the lines to the middle more wiggly, and you get things that look like leaves of a tree, and you get these very complex tilings, and in the end, it's just regular tiling. It's one of the 3 that I showed you in the very beginning, nothing more, nothing less. On the right-hand side, we have a bit more of a trick. When we are cutting out at the bottom, we are not only shifting, but we are mirroring the element and then mirroring it again to put it on top, which means that every second row of elements has to be mirrored. So you get one line of fish looking in that direction, and because the fin below and the fin above are mirrored, you have to mirror all of the line above so that it fits in. So half of the fish are looking to the left and half of them are looking to the right. All of that comes from very easy geometric production lines. The master of this art was probably M.C. Escher, a Dutch graphic artist, 1898 to 1972, who made woodcuts and lithographs. And he also interacted with many famous mathematicians, Penrose, for example, Coxeter, probably a name that is well known, Polya also, a Hungarian mathematician. And he was discovered by the larger world by an article in 1966 in Scientific American. Martin Gardner, famous popular mathematician who ran an own column in Scientific American on mathematics, was featuring him in a large article, and after that the world knew what Escher was doing, and that is things like that. So again, this is nothing else than taking a very simple tessellation and trying with the same methods that I showed you before to subdivide or reshape the borders and so on, and come up with tessellations that look very natural. I mean, the fish on the right are already very impressive. In the middle, if you look closely, different fish are coming together as 6 triangles meet in a triangular tessellation. So in this corner, it's really 6 rather different fish. So this fish comes in with the nose, is similar to this fish who goes out with the tail. So it's very interesting what is meeting here and coming together to form these fish. And I think one of the masterpieces that is often copied is from 1946, that is this knight on a horse, where the legs of the horse also shape the hand of the knight and so on. It's really an impressive piece of artful interpretation of what a tessellation might be. Okay, we're almost there. Last thing that I want to present to you is aperiodic tiling. So far, our tilings were periodic, so we were repeating something, and that made part of the appeal of these tilings, both mathematically, because we are looking at symmetry groups. So there is, in group theory, there is this wallpaper groups and freeze groups that show what symmetry can there be in 1 dimension and in 2 dimensions. And here we go just the other way around. So periodic tiling is repeating patterns. All of our tessellations so far had this emphasis on repeating patterns, and we were defining local patterns and then repeating them in some fashion to infinity. And with this, we were proving that we could, in principle, tile the plane forever. Your football field is 200 meters long, no problem. Our rule will go until the end. Fine. But question is there a tessellation that does not repeat itself? Open brackets, and you can still prove that you can go on forever. This is the last thing that I wanted to show you, and that, oops. And for that, we go back to the definition of tiling. When I was first defining tiling, I said, we analyze the tiling, we select 2 similar points, and then said a tiling is periodic if we can take this one element and move it to the other element, and then everything else covers up neatly. Yeah, the fit should be identical 100%. First thing we can do is we can fake an aperiodic tiling. This is one of the periodic tilings. You see the hexagons, and I could put any hexagon on any other hexagon, even turn it around, and everything would repeat itself. You do that in an infinite plane, and you just take one of the hexagons and replace it with 6 triangles. Then this is not periodic. Yeah, because if you shift, then these 6 yellows go to one of the greens, and that is not allowed. But that's kind of not what we are looking for. Yeah, so that's what I would call a fake periodic tiling. It's not a fake aperiodic tiling. So it's faking this. We cannot do that. So a question that mathematicians were asking themselves is it in the tiles, or is it in the rules, or in both? So the question is, can we find tiles for which you cannot cover the plane with a periodicity, but still you're guaranteed to go all the way, so that you can lay out these tiles, and everywhere you are, you will find a new pattern? Yeah? Is it a tile that defines how my pattern looks like? And actually the answer is yes and no. So the no part is here. Remember the Sphinx? Mm-hmm. The Sphinx can tile the plane periodically. I showed that to you. But what you can also do is you can take, you can take the Sphinx, and from 4 Sphinxes, you make a larger Sphinx. And you repeat this, and you repeat this, and you repeat this. Mathematicians will soon understand that this cannot be periodic, because you're kind of growing from one center, and when you shift, then this center will not fall on another center from which it also grows. So this method of generating a tiling, which is called unfolding or inflating, there are several words. When you start with a small pattern, you make it bigger by subdividing and make it bigger again by subdividing. This kind of guarantees that you're aperiodic. But this is what mathematicians call non-periodic, because this element can also tile the plane in a periodic way. Much the same here. If you take this angle and you turn it around and put it up, then you have a rectangle. So 2 of them form a rectangle, and you could tile the plane with this L shape periodically. Here is also take 4 of them, make a larger L, take 4 of them, make a larger L, etc., and you end up with a tiling that looks like that, and this is proven to be non-periodic. And then came the discovery of aperiodic tiling. In 1961, a guy named Han Wang investigated actually a decision problem. So that's very popular in mathematics, where you ask yourself, after Gödel, everybody was looking for that. We have a question, can we decide that question? And he was, for domino pieces, he was coming up with a way of organizing an algorithm. And he said, well, this algorithm should decide whether a certain question in domino is possible or not. And he said, well, everything works out fine. And then 3 years later, Robert Berger was using this very definition because he came up with a configuration of 20,000 tiles where he said, I put that into your algorithm and the algorithm never terminates, which means it finds a periodic tiling, but it doesn't tell me that it's periodic. So this is kind of, it finds a tiling, but it doesn't tell me it's periodic. So it must be aperiodic. That was the idea of Berger. Here, these 20,426 Wang tiles are the first configuration where indirectly, not by showing that there is an infinite aperiodic way, but by this algorithm that does not terminate, he proved that this is an aperiodic tiling. Further, in the 60s, the set size was reduced to 104 pieces, then to 40, then by Robinson first to 12 in 1971 and then to 6. And then in 1974, Penrose came up with two famous ways of two tiles for which he showed you can only tile the plane with these in an aperiodic way. There is no periodic tiling. And here I show you some pictures of that. So that's the 12 tiles of Robinson. These tiles, they have a lines on them and also small edges in different shapes. And you're only allowed to put them together such that shape fits to shape and line fits to line. So this is part of the rules. You are not allowed to do like long lines of everything if they don't fit together by these color rules. So in a way, the shapes also have a definition how they are to be used. And then you get a tiling like you see on the right-hand side, and this is proven to be aperiodic. You will find areas that look similar, but if you look closely, if you go out, oh, there is a difference. Here is a difference from that. So this is an aperiodic tiling. And with these 12 elements, you cannot tile the plane periodically. This is one of the two Penrose solutions. It's called dart and kite, for obvious reasons. These are the two elements. Of course, with just the darts, you could make a long row of darts, and then the kites fit in, and then another row of darts. But this is not allowed by the coloring rules. Okay, here it is better. So there are these green lines and these red lines, and whenever you want to put two elements together, the red lines must continue and the green lines must continue. So that's the rule, and under this rule, these two elements tile the plane only aperiodically. And the same was true for another two tiles that he was inventing, Penrose, 1974. These two parallelograms. Again, parallelograms, we know that they can tile the plane, but there is a rule how you're allowed to put them together. And under this rule, any tiling, such as the one that you see on the right-hand side, has no periodicity. Seen that, Nena?
Seen that?
Yeah. I'm close to the end. Will work. So, two tiles, Penrose. Yeah, and until recently, until 4 years ago, this was the final answer, because nobody could come up with an idea of saying, I just take one tile, I put it to the floor, bring it together, it covers the plane infinitely. You can go all the way, but you will never repeat yourself. Yeah? And this tile was discovered in 2022. First one, which was called the Einstein hat. You will see, well, Einstein was the mathematical joke on this is one piece, one stone, Einstein. Yeah? And then another one, which was called the Einstein turtle, different shape, but same idea. And then I have to show you why this was not good enough. The spectre tile is the last one to show you. So on the left, you will see this Einstein tile. This tile covers the plane, and whenever you cover the plane with this tile, again, there are rules on how to put it together. When you follow these rules, you can go on forever, but it will never repeat itself. Meaning, you're in a room that is covered with this, you look to the floor and you see a pattern, and you say, oh, over there it looks the same, and you start investigating, and then you will find a difference, because you know, mathematicians have proven it. They've proven that by, on one, an inflation, and the other idea is always we can find upper and lower bounds for how many pieces to use in a tiling. And when the ratio between two kinds of orientations tends to a non-rational ratio, then we can be sure that this cannot be a tiling, because if it's a periodic tiling, you have a period element, and in this period element you have 27 pointing that way and 23 pointing that way, and then in all of your plane it will be 27 over 23. And if you find out that this ratio is irrational, it is not a rational number, then you can be sure that the tiling is aperiodic. Oops, sorry. So, but the problem with the Einstein is it uses only this one piece, but sometimes it uses it this way, and sometimes you have to turn it around. And there were some mathematicians who said, well, that's cheating. Yeah, that's two tiles looking the same mirror image. That's cheating. But within less than 1 year, mathematicians discovered a whole family to which the head and also the turtle, which I don't show you for time reasons, belong. And they found somewhere in the middle of this family the spectre tile. The spectre tile is the one that you see on the right. And it covers the plane, it covers it infinitely, it never repeats itself, and you don't have to turn it around. So it's only one shape, and with this shape, it's aperiodic because in the shape, it's always that you cannot cover the plane in a periodic fashion. So that's what my conclusion is of this talk. I was showing you tessellations to tile the plane. Started out with mathematical characterization, and also by types and by symmetry groups, giving you a bit of impression what is the pure mathematics part behind that. I showed you aperiodic tilings, which are totally different than periodic tilings because it's in their nature not to repeat themselves. And I showed you that these three Einstein tiles, they finally at least solve the question of, is there an aperiodic tiling that only uses one shape? With that, thanks a lot for your attention. I hope you liked the talk. Yeah. There would have been many other things I could have talked about. For example, there is a shape, a single shape, which you can use to run two spirals. You just put them into each other by turning it around in a certain sequence, and they cover the plane completely, spiraling out. I didn't tell you about the sphinx, and that with a sphinx of 1 by 1, you take 4 of them, you can have a sphinx of 2 by 2. With 9 of them, a sphinx by 3 by 3. And give me any prime number, 13. I give you 169 of the sphinxes, and you can do a 13-time enlarged version of the sphinx. The sphinx is a tile which is called reptilian, which has this structure. Perlin, a computer mathematician, was looking at patterns that are not repeating themselves and was getting an Academy Award for that because it's used so much in computer graphics and films. And aperiodic tilings you can also do by just changing the color, and it also looks inspiring. So thank you for thinking with me today.
Oh, thank you very much for the fascinating talk, Michel. Time for questions. We need the, or I could use this one. Yeah. Any questions? Yeah, just use this one so that people online can hear you.
Well, it's not a question, but rather a comment. I find it very fascinating because, like, looking at it, you'd imagine that when you think of filmmaking, right, and how they would like to put the patterns, for instance, of fish, because before you would have to draw many pictures of the same pattern because there weren't any cameras. So I'm just thinking back to how artists were probably using this kind of style for imaging, and also when you're on a computer and you're basically trying to reconstruct an image given certain pixels, what the computer is trying to do is pick up the pattern. So say, for instance, if you're on a quantum computer, you give it half the face, and then it has to reconstruct the full face. So I can imagine how it would try find patterns, and I just thought of tilings. So it's just an interesting way to see where it can be applied. So it was quite fascinating.
So to comment on that, what I showed you with Perlin noise, that really came up when computers started to come into the filmmaking, because things were looking repetitive. When you saw a fish and you had to cover the fish with kind of a pattern, the pattern sooner or later was repeating itself, and people would see that and would say that doesn't look natural. And Perlin came up with a model where, well, the repetitiveness was so far down the road that you could be sure that any fish that you did looked different from fish around them. So they specifically were looking at not non-repetitive patterns, but where the period is really long, so that in computer graphics you don't see, because your eye is so good at seeing things that are matching, that you have to fudge the eye, and you have to kind of steal around that. And that showed up mainly when first computer programs started to go into film.
Thank you. My name is Clinton Kui, and tessellations are really interesting because when you were going through the talk, I was just imagining people are spending a lot of time working on these tessellations for us to kind of understand what's actually going on. So my question is, how do they prove that maybe this particular tessellation is aperiodic? Do they write actual mathematical proofs for it?
Yes.
Or how do they do it?
So there are actual mathematical proofs. The two main proof lines are inflation. Inflation means for the two Penrose tiles, for example, there is a rule where you can take one Penrose tile and you replace it with 4 tiles of Penrose. And you do that with another and you put them together. And then you are inflating this rule over and over again. So kind of you're subdividing, sizing up. Subdividing, sizing up. No holes everywhere, because you make sure that by this subdivision you don't leave any holes. And by this process of subdividing and sizing up, you immediately have a proof that you have a center from which kind of, it's difficult to say with non-mathematical terms, but you have like rays going out from there. And you know when you have a center with rays, that you cannot have another center with rays, and one would go on top of each other, because then sooner or later these rays would meet somewhere. And if you can prove that those rays cannot meet, you kind of have a proof that the translation can never be the symmetry of this tessellation. Most of them have a 5-fold rotational symmetry. That's fine, that's not what we are asking for, but the translational symmetry can never be there. And the other one was the one that I was discussing like on layman terms with Naina. People are looking at larger and larger areas of these tessellations, and they prove that, for example, the ratio between darts and kites approaches the golden ratio. The golden ratio is known to be not a rational number, but if you would have a translational symmetry, you would have a group, and when you shift it somewhere, it just replaces itself. And in this group, you would have a fixed number of darts and a fixed number of kites. and then all of your plane would have this ratio. If you have 107 darts and 204 kites in your atomic element, then all of your plane would have 107 over 202 as a ratio. If you can, on the other hand, prove that the ratio is not irrational, you have proven that the two things cannot come together. Your tiling is aperiodic because any periodic tiling has a rational ratio. These are the two ideas, and to X them out and to write them down is hard. But for example, for the Einstein tile, the proof is up. It's a paper of like 8, now the version is like 8 or 9 pages. It's on arXiv, you can read it. It's readable for mathematicians. It's not that complicated. Yeah, so you can work on that. You can go in a seminar and try to discuss that with your colleagues and find out what is the idea that they used for the aperiodicity.
Some of those guys, I think
Wait for the microphone.
they drew a cap on it, like some tiles will not. It does not exceed 20 possible occurrence of such periodicity. Some you mentioned 20, others you mentioned 22.
Yes. So it depends on the family that you're defining. So for the semi-regular tiling, 8 tilings exist, and you will not find a 9th, because mathematicians have already proven that this is the end of the list. I know a lot of laymen are going there and saying, no, come on, I take a 7, I take something with 7 and something with 9 corners, and then I fudge in some triangles and so on, and it will work? No, it will not. So either it works, or you will have more than 2 of these different vertices. So mathematicians in this area, they're very thorough to say, we tried it all. You use large theorems, like, for example, there is in all plane configurations of polygons, you have a certain theorem that tells you that the number of edges, the number of corners, and the number of faces has a certain relation with each other. And then if you try out, okay, triangles means I have 3 edges per face, they're meeting like that, and so on, you can come up with invariants that restrict the number of elements that you can have. If you only have 2 different types of vertices, you can come up with invariants that say you cannot have more than a square and a triangle and, I don't know, a pentagon or whatever. And if you do that thoroughly through all the lists, you can come up with all of them. Sometimes you can say maybe they have overlooked something, but for the basic groups that I was presenting, I'm pretty sure that enough computer programs were trying to mimic these proofs and searching exhaustively. But yes, there is in the lower ranks of like 8 regular, 9 regular, and so on, there is still room to find some of these tilings.
Thank you.
I think I'll take these 2 questions because you're running out of time. So first.
Thank you very much. Last year, June 2025, I've been interested in this problem of perfect cuboid. And the way I viewed it, it may be settled is if we take the defining necessary right triangles and maybe try to put them down in a way to make a tile. I was able to come up with 26 different configurations, and I was thinking maybe those tiles, they cannot tile the plane periodically, and I was thinking it may be a way of going in that direction. How much do you view it as a promising way to go?
Hard to be answered by myself, because I would say I'm a mathematics communicator. So my own science is not in this area. Yeah? If you ask me something about differential equations and optimization, I would be a person that could give you sound advice. In that area, you really have to talk to people who are doing algebraic geometry or so, and investigating together with them whether this is a viable way to go. Yes, I always encourage students to say, I have a new idea, and how can we fit that together? We've seen over the last years that some surprisingly, some big facts that we knew about were proven to be elementary if you look from the right direction. On the other hand, in a field that is so thoroughly investigated like tilings, I think it's hard for students to come up with genuine own research. But yes, connect to someone who is in that field. Don't be shy. Try to read some papers yourself and try to connect to scientists, sending not immediately 200 pages, but a short mail saying, I'm working on this, can you give me some advice? And you would be surprised how many scientists actually react to something like that. Yeah. Thank you.
One last question from the in-person. Who was it? Okay. Oh, there's a few more. Okay, but afterwards.
Yeah.
One extra.
Okay.
One and then two.
Yeah, go ahead.
You said something about connecting it to group. Like, can you, like, is it like maybe periodic to finite order or something, or a periodic to? And also you mentioned prime number or something like that. I don't know. Can you say a little bit more?
These are very, very general questions. So can you relate that to prime numbers? Of course, there are relations to prime numbers. I mean, this reptile, for example, it's when you put 4 of these sphinx elements together, you can form a sphinx that is double the size. 2 is the prime number. But it's immediately clear that you can repeat the process. So you take these 4, you put them together with 3 others that form again 4, and you can repeat the self, you get 4 by 4, 8 by 8, 16 by 16. When you can double, I'm not surprised that you can go to 16. What is surprising is that you can go to 3, because there is no way that from the way you made from 1 to 2 by 2, how you could take the same idea and go 3 by 3, because it's a totally different way of putting them together. So this is where surprising ideas come, and this is why I was mentioning primes, because for non-primes, if you know how to do it 5-fold and how you do it 3-fold, I can immediately prove that 15 is possible, because it's 5 times 3. First you do 5, and then you follow the idea by 3 by 3. Yeah. So that's why I was saying 13 is also possible, because that's the surprise. 15 would not have been a surprise. So there are relations between symmetries and prime numbers, of course, but that's like a vast field. You can bring in a lot of these things. And as for, what was it, financial mathematics, or you said? No.
The order of the group.
Oh, the order of the group. Again, group theory. I was never strong in group theory. You really want me to go into that? Well, no, I don't think so. I don't think I could reliably make an intelligent comment on that. Sorry. So there was one last question at the very back. You get a microphone?
Yeah, one last from the in-person, and then we go through the online.
Oh,
so just a few more. Hang in there.
I take a sip.
Oh, no questions online. No, good. You can please speak through this one so that people online can hear it.
So my question is not mathematical. I'm not a mathematician. But from an artistic point of view, I would just like to know, visually, I just realized that the one-tile tessellation was organic.
Mm-hmm.
So would you get a one-tile tessellation that is geometric?
Okay, so the reason why it's organic is the following. There are regulations that say how you're allowed to put the spectra together. It's kind of lines on the spectre, and you're only allowed to put them together so that the lines continue. If you do that, then there is a form of the spectre which is a polygon, all straight lines on the outside. But then they came up with a very clever idea. By each of the sides, they could form in a specific S form, so that only the allowed ways fit together. That's why it looks that organic, because the originally rigid shape got some wiggles on each edge so that when you try it out, you can only put it together in the allowed way. This is why it looks organic. And you've seen it from the artistic point of view. If you look at the fish, below the fish is a hexagon pattern, which is very unorganic, I would say. But when you take the edges and you reform the edges, artists can do what mathematicians usually are not interested in doing, meaning to come up with a more organic or visually pleasing way of forming the same tiling. Thank you. So we have some online questions? No.
We don't have a chat. No one is asking online.
Okay.
All right, perfect. So let me just go front. Well, so thank you again for the speaker and for the interesting discussion.
Yeah.
We, of course, can continue it after.
Yeah, I need another 2 minutes of your time. So,
Okay.
yeah. So rejoice when we were talking about this presentation, we said we want to do some hands-on stuff, but this is really difficult in this room. So I want to show you what I have prepared, and I encourage you to take stuff home with you to try that out. So we were attaching to the origami idea that I had before, and I brought some origami paper with me. 2 versions, actually. And some example that directly connects to tiling. So what you can do with origami is also tile a plane. You already start with a plane, which is a piece of paper, and then you fold it in, and if you do it in a way that in the end your result is not a 3-dimensional thing, as we did last time, but a 2-dimensional pattern, there are origami shapes that just repeat themselves. It's hard to see, but I hope you can see it here. This is one piece, no cuts. It looks like it's folding over itself, but it doesn't. And on the other side, it has also a tiling with triangles and squares that can be repeated forever. And I prove that to you by showing you the basic element. This is what I would have done with you if we had more time, which is a square on top of a plane, and if you fold it together, you can see that the square is rotating to get into the shape that it wants.
Just one.
Yeah. So if you fold it out, you can see that the square in the middle is rotating and folds together in this. If you connect one square with another mirror shape, you can make a long line to infinity. And if you do it in the other direction as well, you get a plane. And then try it again. Here you are. Yeah, that's good. So this is a 9x9 pattern of squares. All of them, you can take them apart to rotate. And in and on itself, they form 2 patterns on the side. And can you go back to my presentation for one slide? If you look online for that, it's called the origami square twist. You're folding all these horizontal and vertical lines, then you mark some of the lines to have a mountain fold and a valley fold, so a fold upwards and a fold downwards. And then more or less magically, if you push it together, the square twists and you get this square element that I showed you. I have a pack of paper with me. You can grab 2 or 3. We have enough. I have like 300 pages. So you can, each of you can take 2 or 3. I put them to a desk outside. And if you want to look up origami square twist, there are wonderful YouTube videos that explain to you how to fold that. So we are not folding it together, but I give you this exercise for at home, fold an origami square twist. And with that, I'm done for today. Thank you.
Thank you very much, Michelle, for the nice talk and also for the gift. So we will surely get some papers home. Thank you.
So,
Just a few things from my side. We are now joined by so as I said earlier, this is done in collaboration between AIMS and NITheCS, and now we are joined by the director of NITheCS. So, Francesco, would you please say a few words, Professor Francesco Petruccioni.
yeah.
Please tell us a bit about NITheCS, just a little bit.
Yeah.
You're gonna have to talk through these boxes.
So good afternoon, everyone. Sorry I missed the beginning of your talk, but I sneak sliding silently from the back. No, welcome to Stellenbosch. Those of you that
Let's do this. This was on, but you could probably have to speak a little bit louder. Oh, that one works.
That one you need for the online people.
Okay, so all very complicated.
Yeah.
Okay, yeah. No, thank you. Welcome to Stellenbosch. Those of you that haven't been to Stellenbosch before or not residing here, and to some old Stellenbosch inhabitants that I can recognize here in the audience. Yeah? As you know, NITheCS is a relatively new national research facility in South Africa, and it is a consortium of all universities in the country and AIMS. Yeah, so NITheCS and AIMS are sort of part of the same family. Yeah, and the name says theoretical and computational sciences, and essentially is everything and a little bit more. Yeah. So one of our mandates is also to do engagement and training. So we do lots of online events, and you're welcome to go to the website that you probably find somewhere at the bottom of that poster and join the mailing list. All we offer is always for free. Yeah, at the moment we have an introductory Python course, and there are 800 participants. Yeah, just as an example. Yeah? And we were very happy to have the opportunity to join AIMS in organizing this event. So it seemed like it was a lot of fun. So thank you very much to the speaker, and hope we will see you again in action. Thank you very much. Thank you.
And now I would like to invite the Executive Director of AIMS, Prof. Karen Howell, to deliver the closing remarks.
Great, thank you everyone. I'd like to start my vote of thanks by asking Dr. Rejoice Gabi-Molefe, our House of Science Manager, just to come forward to say a word of thanks to Michal.
Thank you so much, Prof. Karen. Good afternoon, ladies and gentlemen, and honorable guests. I can't hear you. That's much better. All right, so I'm just here to give thanks to Dr. Winckler as a token of appreciation. So we have been collaborating with Heidelberg University since 2016. So we just want to thank you for your leadership, for your drive, for internalization, teaching, research, and most importantly, communicating your mathematics.
Thank you.
Thank you so much. At AIMS, we really recognize that mathematics is a driver of our economy in this country, but it can't play that role if we don't share our mathematics knowledge to the public. Hence, we are here. So we value your passion, and we hope that we are going to continue our collaboration. So this is the third public lecture he's giving. He did two at Muizenberg, and this one with NITheCS. So thank you so much for your passion and drive for mathematics.
Thank you. Thank you so much. Yeah.
All right, thank you, Rejoice. So from our AIMS side, I'd like to thank everyone for joining us today for this very special AIMS public lecture. It was a wonderful gathering of ideas, energy, and community. I'm also extremely excited that it's our first formal collaboration of a public talk hosted by NITheCS jointly, so thank you for that. My sincere appreciation to Naina Rolavasowena, I'm going to try, for an engaging and thought-provoking talk about his journey at AIMS and his journey subsequently. He's an alumni that we're extremely proud of. We all cheered for him last year when he promoted, and he's one of our favorite success stories. So thank you for being here today. Heidelberg University, we want to thank for the support and for the partnership again, and thank you, Michal, for this lovely talk again and offering your time during a very busy week. Thank you to Francesco for his contributions, and to Renee Kortzer and her team at NITheCS, who've been phenomenal in pulling this together and organizing all the finer details. Today's event beautifully showcased the legacy of partnerships that continue to strengthen our scientific community and expand the reach of mathematics across institutions and borders. We have representatives here from all across Africa and Europe, all coming together to discuss mathematics. Finally, a very special word of thanks to our AIMS team. I just want to also recognize Rejoice for all the communications from our side and the arrangements our administrative team made to get all our students here today. Thank you for being here and ensuring a seamless and welcoming event. I also want to celebrate our students who, during a very busy block, got on a bus and wore your shirts and came out to Stellenbosch. I really appreciate your time and effort to be here, and I hope you've enjoyed this very nice talk. As we celebrate these long-standing collaborations, I also want to highlight a new partnership we are very proud of. One to contribute to AI literacy across Africa, and it is the AI Research Foundations for Higher Education project. It is a project with support from google.org that AIMS has partnership with. It's going to empower universities to lead Africa's AI future. Oops. Oh, sorry. And in the following way. So the plan is to leverage AI Research Foundations to receive full support for universities to teach AI to their staff and students. So there's a grant of up to $57,000 via google.org for each university to send some lecturers for training. Fully funded workshops for lecturers and teaching assistants will be hosted at AIMS, and there'll be a blended learning lecturer toolkit that is developed and offered by University College London. I'd like to ask Yassi just to stand up. So Yassi is here representing the team at AIMS who will do the training. They're very excited to be here. So if you'd like to ask more questions about this program, please talk to Yassi, or you can also scan the QR code.
Big button, yep.
For more information. So if your university is maybe interested in joining this partnership, please connect with AIMS. We'd love to hear from you and see how we can connect. Thank you very much. So in closing, I just want to ask all of you to join us for a big group photo outside, and then there's some tea and snacks catered afterwards, tea and coffee for those of you who need to stay awake. I'm also very proud to say that we have a number of our AIMS alumni who have subsequent positions either at SERI or SESIMA or just working around Stellenbosch who've joined us. I see them at the back. They've come through, so please also make time during tea to chat to them about their AIMS journeys and learn from each other. So on behalf of AIMS and NITheCS, thank you very much for joining us.
Thanks a lot. Interesting. Yeah. I somehow suspect somewhere there's some rational, irrational argument goes in there somehow.
Yeah. Yeah, that's